Good morning. Imagine you have a flashlight and you place it on a hill 2 miles away, and you come back in a position where you can observe that flashlight. Now imagine a moth flies in front of that flashlight, and you want to be able to determine when that moth flies in front of the flashlight. Now, tell me what color is that moth's wings? So that's a good segue into my discussion today. I'm discussing the evolution of exoplanetary characterization. We start with the transition from Hubble Space Telescope, which is our optical pioneer, to the James Webb Space Telescope. So Hubble provided a great many years of pictures and uh, scientific data that we had no clue existed before Hubble. And it had coverage from UV to near infrared. James Webb Space Telescope represents a revolution with its 6.5 meter mirror versus the 2.4 meter mirror of the Hubble Space Telescope. And James Webb Space Telescope has a much larger spectral range, which goes deeper into the mid infrared. So you can imagine Hubble is looking through a tiny keyhole versus James Webb Space Telescope through an entire window. The overarching goal is to move from simply detecting, just basically knowing that a planet is there due to its light curve, which is when a planet transits in front of its host star, there's a light dip. And for years, we were able to detect that exoplanets existed just because of the light dip. But now we're looking at true characterization where we can map the physical and chemical properties of these atmospheres. For years, was hampered by guesswork. Basically, we would plug it into a computer, and if certain criteria were met, we assumed that that's what that planet was made of. So the transmission spectroscopy, that's our primary tool. During a transit, the host star acts like a backlight as light filters through the atmosphere, the little bit of translucent annulus of the exoplanet's atmosphere. Um, Specific molecules absorb distinct wavelengths. So by capturing this with a spectrograph, we can decode the molecular fingerprint of that distant world. So we are basically saying, okay, this planet has this type of atmosphere uh, through through a spectrograph or analyzing a spectrograph instrument and the readings from that. So we can actually tell what that atmosphere is made of. This is all governed by something called the scale height, or H, as it's going to be referred to. It's our governing equation. H is equal to the Boltzmann constant times the atmospheric temperature divided by the mean molecular weight and the surface gravity. So H is proportional to temperature and inversely proportional to molecular weight and gravity. So, put simply, hot gas giants with low density atmospheres have a much larger, like a puffier target that we can shoot through that is much easier for us to detect than the tightly compressed atmospheres of cool, rocky planets. So, a gas giant will have more atmosphere and more of a fingerprint, so to speak, to look at. It'll be much higher versus a rocky planet where that atmosphere kind of hugs the surface a little tighter, and that makes it much more difficult to analyze. So Hubble had a narrow window, which led to something called model degeneracy. because we were looking through a narrow keyhole, like very small portion of the spectrum, different atmospheric conditions like clear skies versus high opaque clouds. They could produce like the same flat signal, and we couldn't break these degeneracies with data alone. We had to guess, and that goes back to what I was saying earlier. We had to plug these into programs, and if certain parameters matched, we just assumed that that's what this planet was, or what this planet's atmosphere consisted of. So James Webb Space Telescope solves this by expanding our coverage into the mid-infrared. So by accessing these longer wavelengths, we aren't just seeing like a fuzzy picture of it. We're capturing the actual distinct molecular signatures of this atmosphere. This allows us to resolve the degeneracies that limited Hubble and provides a continuous high-resolution view of the atmosphere. So we get a much better picture, a much more accurate picture of the atmosphere. So the study, WASP 39b is the easy mode for this study. It's a hot, like large Saturn mass gas giant. It provides a huge signal, like a massive signal to read from. James Webb Space Telescope's near-spec instrument allowed us to perform simultaneous robust detections of water, carbon dioxide, carbon monoxide, and sodium, and is finally giving us a clear picture of its composition. One of the most exciting findings was the discovery of sulfur dioxide. We saw a prominent absorption peak at 4.05 microns that static models did not predict. This provided concrete proof of active photochemistry going on. So where the UV light from the host star breaks down molecules to create new ones, and this proves that the atmospheres are dynamic and living chemical systems. So now we face a hard target, rocky exoplanets. Like I was saying before, these are much harder to detect the atmospheres. There is a high surface gravity and cooler temperatures that compress the atmosphere, making the scale heights very small. So the challenge is the 5 scale height barrier, where we need extreme precision to extract those tiny signals from the stellar noise. So we are extracting a very tiny signal from a very noisy sun, so very difficult to detect. So there's a large leap in our capabilities, and it's best seen in our confidence levels. For water vapor, Hubble achieved a detection significance of about 3.2 sigma. With identical simulations, James Webb Space Telescope NERISIS instrument pushes that confidence to 8.5 sigma. So we're no longer working at the edge of detection. We're working in the realm of high precision science. So we're solving old problems and uncovering new ones, shifting of scientific horizons. Um, So while James Webb Space Telescope has effectively resolved the wide wavelength guesswork, the limited it limited previous missions, its pristine data quality has unmasked deeper, more intricate physical challenges. There's stellar contamination, like I said, with bright stars. So uncompromised data means uncompromised views of the host star itself. Signals from star spots can easily warp or fake molecular spikes in the exoplanet spectrum. The star spot barrier, subtle uncorrected electromagnetic signals or cold spots on the stellar surface can easily warp transit depths, faking or obscuring critical molecular absorption spikes in the resulting exoplanet spectrum. So we're deconstructing the diminishing returns here. The 1D model limitations, historical inverse atmospheric retrieval models rely on a simplified one-dimensional averaged calculation of the atmospheric column. So that goes back to what I was saying, we would have to kind of guess. They're intricate 3D realities. Real exoplanetary atmospheres exhibit highly complex three-dimensional dynamics, including localized cloud decks, morning to evening terminator variations, and severe horizontal temperature gradients. So really, there's so many things that have to be taken into consideration, not only distance and light noise. There's even the time of day for that planet that could vary how we read the atmosphere. And there's parallel interpretations. So we have to use models, complicated models to avoid like systematic biases and abundance estimations. So looking ahead, we're moving from the James Webb Space Telescope era of discovery to a future of direct characterization. The LIFE mission, using a Knowling interferometer, will allow us to suppress the light of the host star directly, bypassing the lucky alignment requirements of transits to sample rocky atmospheres. So it will basically block out the host star, making it much easier, like putting your thumb over the sun, and you're able to see the outside or the atmosphere of the sun. You're blocking that light out, which will make our life a whole lot easier when we characterize these rocky planets. So, in conclusion, JWST didn't make exoplanet physics easy. Instead, it just moved the goalposts for us. We've shifted like what we questioned from being limited by our instruments to now grappling with the complex three-dimensional physical nature of these worlds. So we've graduated from statistical guesswork to the era of planetary science. So, we've moved past guessing what we are actually looking at, and have kind of presented more problems here with our better detection. So we're in a new era of exoplanet discovery and what we know about the universe. And there are my references.